Hi everyone, my name is Pardis Emami-Naeini. I'm an assistant professor of computer science at Duke University. Today, I'm super excited to present our work on measuring consumers' monetary value of security and privacy improvements for their smart devices. This is a joint work with my colleagues Janarth, Yuvraj, and Lorrie at Carnegie Mellon University. Smart device manufacturers are not transparent about their devices' security and privacy practices. Over and over, we see these companies collecting more data than promised and needed, and sharing this data with parties that consumers are not informed about. One way to potentially incentivize device manufacturers to improve their practices would be to show that if the information is provided when doing comparison shopping, consumers will value more privacy-respecting and protective smart devices. To measure the monetary value of security and privacy improvements, we conducted a two-phase survey with US prolific participants. Phase 1 looked into the monetary value of individual security and privacy improvements, while Phase 2 explored the value of transparency when multiple security and privacy practices were presented to participants. In both phases of this study, we simulated a consumer purchase setting, where participants were asked to compare two models of the same smart device and specify basically which one they prefer to purchase. One model has a lower security or privacy practice. The other one has a higher level of protection. For example, a smart speaker with no security update compared to a smart speaker with automatic security update. To measure the monetary value of each security or privacy improvement, we explored the trade-off between the amount of compensation and the level of protection, device protection. In other words, we made participants believe that by selecting to purchase the more protective model, they will receive a lower compensation. In both phases of our study, we use IRB-approved and critically designed deception elements, which were critical for our experiment. First, we introduced our survey as a market research study that we are doing in partnership with a major retailer to inform their market strategy for future soon-to-be-released models. We actually designed the specifications of these hypothetical models. We told participants that their only compensation would be a discount coupon to purchase these new models. However, these devices were hypothetical, therefore the discount coupon could also not be a real thing. To compensate, at the end of the data collection, we sent participants $10 bonus through Prolific. At the end of the study, we debriefed all participants and provided detailed explanation as to why certain elements of deception were used. We tested improvements regarding 5 security and privacy factors: type of access control, the identifiability of data stored on the cloud, the parties the collected data is being shared with, purpose of data collection, and availability of security updates. For each factor, we selected 3 levels: the least protective, medium protective, and high protective. For example, for security update, we selected no security update as the least protective, manual update as medium protective, and automatic security update as the most protective option. We selected these values based on our prior research. To measure consumers' value of these security and privacy practices, we created 3 comparison pairs for each factor. And since we had 5 factors, we ended up with 15 pairs. The format of each pair was a higher protective value versus a lower protective value. For example, for security update, we tested manual versus none, automatic versus none, and automatic security update versus manual security update. To measure the monetary value of each of these improvements, we used an incentive-compatible method called multiple price list, which I will explain in the next slide. With a simple example, let's very briefly talk about what a multiple price list is and how it works. Let's assume that we want to estimate how much of a premium consumers are willing to pay to purchase a smart device that receives automatic security update compared to a smart device that receives no security update. As the name suggests, multiple price list shows a list of prices presented in a table. Participants were asked to answer the table row by row, and for each row to specify their interest in purchasing 2 models of the same smart device. We designed the specifications ourselves, so we made sure that these 2 options are identical in all aspects, except for the security or privacy factor that we are testing. In this case, security updates. The risky option is always on the left column. The more protective option is on the right column. The amount of discount coupon for the first row is identical for both options. For the risky smart device, the discount coupon will always stay the same throughout the table, while we decrease the amount of discount for the more protective option as we go down in the table. Based on how participants fill out this table, we are then able to identify the minimum and maximum amount of premium they are willing to pay to have that tested security or privacy improvement. In this case, receiving automatic updates versus no updates. Let's assume this is how a participant fills out the table. We told participants that 1 row will randomly be selected and their selected amount of discount, and they will be compensated with the selected amount of discount. This random selection is the main reason as to why multiple price list is incentive compatible, and why it makes sense for participants to be truthful when stating their purchase preferences to maximize their compensation. In this example, up until the 3rd row, the participant preferred purchasing the more secure option, even if they have to lose some amount of discount. Based on the table, this participant is willing to lose $1 discount or willing to pay $1 premium, but they are not willing to pay $2. Therefore, the desired amount of premium is between $1 and $2. So basically, we are looking to see where participants switch their behavior. As I previously mentioned, regardless of how participants answered the survey, we compensated them all with $10. Now, let's talk about some exciting findings. We tested 15 comparison pairs, but for the sake of time, let's just go over the 3 most valuable security and privacy improvements. For a $60 smart speaker, the most valuable improvement was having de-identified cloud storage compared to an identifiable cloud storage, which was around $12. The second most important, most valuable practice was having password access control compared to having no access control. And the third most valuable improvement was having multi-factor authentication compared to no access control, which was around $11. Although our participants were willing to pay significant premiums for the majority of tested security and privacy improvements, there were a few exceptions. Based on the qualitative findings, lack of usability was the main reason as to why some security and privacy improvements were not as valuable. For example, we hypothesized that multi-factor authentication provides more protection compared to password. Therefore, participants should be willing to pay more to purchase a device with MFA. However, our participants, despite acknowledging the added protection of MFA, they found it to be less convenient. Therefore, they were willing to pay more to purchase a device with password. A participant said, I know that multi-factor is probably more secure, but being able to change the default password is easier. In addition to measuring the monetary value of individual security and privacy improvements, we also explored how much a security and privacy nutrition label that provides transparency over all these 5 factors is worth to consumers. We tested 3 types of transparency: most protective, least protective, and no transparency. We set the most protective label to consist of all the most protective levels of these factors. The least protective label to include all the least protective values of all the 5 factors. And in the no information label, we set the value of the factors as not disclosed. Using multiple price lists, we then measured how much each type of transparency is worth to consumers. Findings showed that, as we expected, providing a label that communicates the most valuable level of the factors is most valuable to consumers, basically. So they are willing to pay the highest amount of premium for that. But the finding that was surprising here was that putting a label by itself is not enough. Our participants were willing to pay significantly more to purchase a smart device that provides absolutely no transparency compared to a smart device that they know is very risky based on its label. This finding is not just interesting, but potentially very important. As it suggests, if transparency is not mandated, device manufacturers that do not care about security and privacy may decide not to disclose their practices, not to sway consumers away from purchasing their risky products. To conclude, in a 2-stage incentive-compatible experiment, we showed that if the information is readily available, consumers would significantly value security and privacy improvements, given that these practices are still usable and convenient. Our findings suggested that to be effective, transparency should eventually be mandated so that device manufacturers can get penalized if they have risky practices. Following a presidential executive order, smart devices in the US soon will come with security and privacy labels. Together with my colleagues at CMU, we are using our extensive empirical research on IoT labels to inform the key stakeholders involved in this program, including the White House Consumer Reports and Consumer Technology Association. With that, I would like to conclude my talk. Thank you very much for your attention, and I will be happy to answer any questions now.